So in this video, I'm going to use the Maxwell construction to plot the two-phase envelope superimposed on our PV isotherms from part 3. So this right here is the Maxwell construction, and it is basically a line on our isotherms from before that we plotted right here. And what it does is it splits it so that these two areas are equal. And what I'm going to do in this video is plot this solid line here using those areas. So what we first need to do is take the integral of our line in order to get these areas. So what we're going to be taking the integral of is this generic cubic equation of state that we use to plot these lines. So I'm first going to define a function for the areas, and I'm going to need to input pressures and temperatures into that. And then I'm also going to define a function for the integral of our equation of state. Integral. And that's going to be the integral with respect to the volume. So to take this integral, we are going to use Wolfram alpha. And to make this typing in easier, I'm going to make this split screen. Oh. Okay, so we want the integral of, and we're going to put it all on one side, so p minus RT over V minus B minus A over V plus E times B times V plus S times V. And this will be our answer. So now I'm going to enter this answer into our integral. So to make that easier, I'm going to minimize this again. And type it in here. So equals negative A times B, the log of B times S plus v plus a times log of e times e plus v plus b times p times e minus s times v. And I can get rid of that parenthesis and this parenthesis. So then all that divided by b times e minus s and then all of this will be minus r times t times the log of b minus v. So I'm just going to check that all of the parentheses match up. I'm just going to put a parenthesis around the whole thing as well. Alright, and then now we're going to have to define our A, B, E, and S again, so I can just copy that code from up here as well, like that. So I noticed a few mistakes in this integral. First, there needs to be another parenthesis here, and at the end. So that now this A isn't negative, and then this will be minus. And then also there should be another parenthesis here to close that off, and then another parenthesis here, and then we can take that one away. And then this b minus v needs to be the absolute value of b minus v, so that the inside of this logarithm is not negative. And then this parenthesis should not be there. So then we have this parenthesis matching up there, that one there, this one here, and this one for the whole thing. And then now we can return this integral. So now we are going to actually need to call the integral function within our area function. And we're going to use our cubic roots from this cubic v function for our integral function. So first we need to call this cubic roots equation or function first. So the cubic V for pressure, temperature, and that's going to give us 3 volumes, and we are going to want, I'm going to make this full screen as well. We are going to want to unpack those 3 volumes individually. So volume 1, volume 2, and volume 3. And then after that, we're going to want to use these volumes to construct our areas. So as you can see from the Maxwell construction here, we're going to use the first volume, or actually we're going to use the second volume minus the first volume integral as our bounds for the first integral to get this area. And then we're going to do volume 3's integral minus volume 2 to get this area here. So in our code, let me make this full screen. So our left area here, our left area is going to be equal to, integral of v2 minus integral of v1. So integral of v2 minus integral of v1. And then our right is going to be equal to the integral of v3 minus v2. v3 minus the integral of v2. And then we are going to want to return these areas. So return left and right. So our next goal is to get the pressure at which these 2 areas equal 0. So to do that, we're going to need first to define a function that will get the difference, or really the addition between, because one's going to be negative, one's going to be positive, between these 2 areas. So I'm going to call that the area difference function. And we're going to want to enter just vector values, but in our case it's only going to be the pressure. So the pressure will equal our vector. And since it's only going to be one spot in the vector, we're going to put the 0 there. And then we are also going to have a temperature argument as well. And then now to get the difference between the areas, we're going to use our area function up here, and we're going to add those left and right areas. So first I'm going to call our area function, areas, pressure and and that's going to be equal to our left and right. And then we're going to want to return the addition of these, so left plus right. So now, in order to get where these equal 0, we are going to use the root function. So I'm going to import it. So from SciPy optimize import root. And so we're going to use this root function, and the function we want to find the root of is this area's difference. And then the argument we wanted to use is the pressures. So I'm just going to input a guess for that, and it's only going to be one pressure, obviously. So I'm going to do like 1 to the 4th pascals. And then we are also going to need to input the temperature as well. So that will be, and to do that, we can use the args, which is just an additional argument that the root will use. And we can just try like 373.15 Kelvin. And this is supposed to be area's difference. And then as you can see, it outputs a bunch of stuff, but what we want is this x part here. So I'm going to put dot x, and then since it's an array as well, and we just want this first number, I can put to get the first number, and then so this will be our pressure that we are looking for. So now we are going to work on getting our numbers to plot this. So first we're going to need to get our pressures right here, and to do that we are going to use our root function that we just made. So our vapor pressures are going to be equal to this root function. And instead of just using one pressure, we're going to want to iterate through different pressures. So I'm just going to call this our P guess. And then also we're going to want, instead of just one temperature, we're going to want a bunch of different temperatures. So I'm just going to call this T. And then, so now we can define our volumes as well for this, our volumes. And those volumes are going to come from our function up here, our cubic V function right here, that gives us those 3 volumes. So we're going to be using just the vapor volume right here and the liquid volume. So the first and third volumes it'll give us, and not the middle one. So we're going to call our function up here our cubic v function. And we're going to use our pvap and then our temperature. And again, we are going to want the liquid volume and vapor volume, which will be the first and third. So that, and then we are going to need the second one, so I'm just going to put a placeholder underscore there, and then we're going to need the vapor volume as well, so I'm just going to call it gas as well. So now at this point, all we need is our temperatures. And for our temperatures, we're going to want a lot of values in this range where it is curving. So I'm not going to do linear space temperatures like we did before. Instead, we're going to model it off of 1 minus e to the negative x function, exponential function, that'll give us more numbers in this range with the curve and less in the beginning. So our temperature is going to be equal to the critical temperature and then plus 275 Kelvin, and then we're going to multiply by that 1 minus e to the negative x function that we want to model our temperatures off of. So 1 minus numpy exponent to the negative x and then we are going to add that 275 back, and this should be subtraction. And finally, we are going to need to iterate through different x values for this temperature. So for x in range, and just going to do like 0 to 7 and get about like 500 values. Like that. So now I'm going to create lists for our pvap, volume liquid, and volume of the gas in order to have a huge range of values for our plotting purposes. So I'm going to create a pvap list, and it's going to start empty, and then a liquid volume list that'll be empty, and gas volume list that will be empty. And then we are going to add to these lists using our calculated pvap each time, and then our liquid volume as well. And then gas volume as well. And then finally, we are also going to we need a value for our P-gas as well. So initially, we're just going to go with a very small value, like 100 pascals. And then each time we iterate through this, we want it to we're going to make sure that our P-gas is less than our P-VAP. So we're just going to use the last P-VAP as our P-gas. And I forgot a colon there. There we go. So now if we were to plot this now, it would not work because we have the volume liquid and the volume gas. So we need to combine those lists to be able to plot. So our V for plotting purposes, I'm going to call it, is going to be equal to the volume liquid list plus the gas list with all the rows, all the columns, but we're going to want this backwards. And then our pressures for plotting is going to equal the P-VAP list plus P-VAP list again with all the rows, all the columns, and backwards. So now we can copy our plotting from before, and then we're going to change it to fig 2 so it doesn't get confused with our other figure. And then we're going to add a new scatter outside of that loop, where our volumes will be V plot, pressure will be pressure plot, mode lines, name, I have to call it the Maxwell. And then I'm going to make the line color white. And it looks like we are just getting a flat line there. So there must be something up here. Yeah, so our x's should be linear space, so then we get our curve right there. So I'm going to make this lumpy.linspace instead. And let's see what that does to it. And there we go. Now we have our nice little curve there on our plot from before.